So, so today we will discuss complex measures. Okay, so okay. Well, complex measure is just a sigma additive function. So it is a definition. So it's denoted by mu. So we have a sigma algebra X. We have a measurable space, a space where we can define measure. A function, a set function, a mu set function mu from script f to c is a complex measure. If, of course, first condition should be mu of singleton should be 0, and it's countably additive. Okay. Of course, this way you can define this measure on any linear space. You can take a Banach space or something, operator space or whatever. You can define this taking values in any Banach space and work with that. So such things you can do. And in the next course, we will see that. And in the second course, we will define up measure taking values in projections. We discussed projections in the last class. So we will discuss measures taking value in projections. Okay. So you hear me?
Yes, sir.
Okay, I'm not able to. Okay, so this is countably additive. That means that is if we have en a sequence containing in script f, and ens are disjoint. Then summation, then mu of union of union equal to summation mu of union. That's all. It's a countably additive function. Of course, with the measure of empty set is 0, and it takes values in complex numbers. So it's a real measure or a signed measure. If a real measure, the same property with real measure, a signed measure. If mu takes values in mu of a is in real for all a. Okay, it's the same problem. So this is what we call as complex measures, and we want to study its property. So given a complex measure, we want corresponding to that, we want to talk about a positive measure corresponding to that, and using that. So the whole, this class will be devoted to, so given any complex measure, so notice mu equal to mu of a equal to real part of mu of a plus I times imaginary part of mu of a, and these both are signed real measures. Okay. Assigned measures or something, real valued measures. I mean, if that is countably additive, then this is countably additive because real part and imaginary part, they have to coincide. So real valued measures. So it's enough to study these things. So we know that any complex measure can be written as a real part and imaginary part. So we have to study the real measures. So once we want to prove that any real measure to prove any signed measure, any real mu equal to mu plus minus mu minus for some positive measure. Whatever we called as measure, this is what we called as measure, positive measures, mu plus or minus. Okay, that's what we want to prove in this class. Okay, for that we want to define, so finite, for any finite positive measures. So notice that when we talk about complex measures, we don't allow the value infinity. In positive measures, the value infinity is allowed. Here we cannot allow infinity because infinity minus, it will not be well defined. So we are not allowing infinity. So the question is whether we can write it as a decomposition mu plus minus mu minus or finite positive measures. So that is what we want to prove. So to prove, so corresponding to any real measure, we want to define what is called a total variation measure, which is the total variation, which is more or less same as what you call as total variation for a function. You make a part, say in function, what you do, if you have an interval, you make a partition, all sorts of partition, and consider the difference. I mean, f of xi plus 1 minus f of xi for each interval, and take the modulus and sum it over all possible parts. I mean, then it should be, the supremum should be finite for all possible partitions. We are going to do the same thing here. We are going to define the supremum. So before that, I want to define the following. So we want to prove this lemma. So the lemma is following. If you have any sequence of pairwise disjoint containing it. So we always assume we have a measurable space, X script F, a sigma algebra. Then for any En disjoint, okay, we consider this summation n equal to 1 to infinity mod mu of En is finite. Okay? That's what we want to do. I mean, we are taking the mod here. Okay, so what we have is, so we can assume it's a real measure, but here now it's a complex measure. Okay, mu is a complex measure. From the next proposition onwards, after defining the total variation measure, we will talk about only real measure, and we will prove something for the real measure, and it will follow for complex measure also. Now we consider mu is a complex measure. So for a complex measure, we take any partition, countable partition, any countable disjoint set, not partition, countable disjoint collection. Then this sum is always finite. Okay, and this is just easy. Let an, you call an equal to, so incidentally I am just following the book by Sundar where this complex measure is done. I will slightly change few things, but essentially the proofs are same. I may not go in the order that is mentioned, that is given there, but it's the same thing. Okay, at an equal to en if mu of en is positive, okay, greater than or equal to 0, and it's empty set if not. Okay. Similarly, we define Bn equal to again En if mu of En is negative and equal to if not. So now we know that An and Bn's are disjoint. Okay, and we know that so since they are disjoint, I mean it's I mean when this is non-empty, that is empty. When that is non-empty, this is empty, and we know that summation En equal to, so this is purely negative, that is purely positive. So this is equal to summation n equal to 1 to infinity mu of an plus summation n equal to 1 to infinity. The mod is outside mu of bn. Okay, because this is purely negative, so you have to put the mod outside. Okay. But we know that these are all real.
Sir?
Yeah.
Sir, yes. Here mu is a complex measure, right? So what do you mean by mu of en greater or equal
correct.
to 0?
Correct. Mu is a complex measure. So, okay, then we have to take the signed measure. So what do we do? Okay, so let's assume you are correct. So from the next proposition, so we take it to be signed measure. We prove it for signed measure, then it will be clear for complex measure. Okay, so maybe I will assume complex measure, and then we will prove in the later. I mean, initially in the proof we will assume it's a signed measure, then we will prove it for complex measure. Mu is a complex measure. Okay, good. So mu is a complex measure. So first assume mu is real. Okay, we'll prove this for real, and then we will prove for complex measure. Okay, which will follow. Okay. So shall we do it in the end? Let's see. I think it will work. So once we have written it like this, then we know that summation n equal to 1 to infinity mu of an is something, a real number, and summation n equal to 1 to infinity mu of bn is also a real number. Okay, so this whole thing is less than infinity. So they are just real numbers, and of course they are. I mean, They are just finite real number. Because of that, this is infinite. This is, I mean, this is just the union. I mean, if you want, you can write it as this is equal to mu of union of an plus mod of mu of union of an. Because of that, this is real. Okay? So because of this, we know that they are finite. So suppose, so it's proved for signed measure. Okay. So this is proved for signed measure. Suppose mu is complex. Then what happens? Mu is complex. Then, so is it just less than sum of that? Mod mu of e. Is this not true? Less than or equal to mod of real part of mu of e plus mod of imaginary part of mu. This is true, no? Because of that, this is true. So both those things are real numbers, right? This is just triangle inequality or something applied for complex numbers, corresponding complex numbers when you have I. So okay. So we have proved this. So we proved the summation, which makes sense for which is a real number. So for any disjoint set, the summation makes sense and it's a real number. It's a finite positive real number. So we can make sense of the summation for any collection of disjoint sets. Using this, we make the following definition. So here mu is a complex.
Sir.
Yeah.
Sir, how did we prove that mu of union AN is and union BN is finite?
That's the definition of measure. The measure is a real valued measure. Measure is finite. Only when you take the modulus of the disjoint, it may blow. I mean, it doesn't, but it may blow up. It's not clear. So that is why we have to prove. The measure is a real valued measure.
Oh, yeah.
So when you take modulus, it's a finite positive number. Okay. But when you take the summation, see this summation, whatever the summation we have here, summation n equal to 1, mu of En is finite. Okay. That's because it's countably additive. So that's going to be union of that, and that's finite. Okay, but when you take the individual modulus and sum it, it may not be finite. That's why we have to prove that. Okay, that's the only. Yeah.
Yes, sir.
Okay,
Thanks.
that's all. So now then we have proved for a complex number. Okay, so once we can make sense of that summation for any collection of disjoint set, we define the following, which is called the total variation measure. Mu is a complex measure, and E is a set, is a measurable set. Then define mod mu. Mod mu is the new measure we want to define. Mod mu of E equal to supremum of all En disjoint collection, which is contained in this, and union of En equal to E. Okay. Summation n equal to 1 to infinity. You take all those summation, which we know it's all finite, then you take the supremum. Okay. Of course, this may be infinite. We are not worried about it. We will prove that this is finite. That's what the idea of this whole class is.
Sir, your voice is breaking off.
Voice is breaking. Okay. So you ask me to repeat. I cannot do much about it because it's an internet problem. I don't have a very nice internet connection. I will try to change it. Okay. But for the time being, this is the internet I have. If you don't hear anything, you ask me to repeat. Okay?
Yeah. Can you repeat the last part?
So the last part is I am just defining a new measure. If you have a complex measure, then I'm defining a new measure called mod mu, which is defined as you take this summation n equal to 1 to infinity mu En, and you take this supremum over all possible disjoint set whose union is E. That's all. Okay. Maybe I will. Union of En equal to 1 to equal to E. Okay. But do we need disjoint? I don't know. When we see, but oh yeah, that's yeah. But
Sir, equal to E or contained in E?
equal to E. Contained in E, I mean, when you take the bigger thing, it will be, I mean, it's just a disjoint union. It's equal to E. I mean, if it is contained in, it will be smaller, no? Because you are taking mod. You will be having more sets when you add something, right? So it's better to take E.
No, sir. What I thought was, can it be like the union will be exactly equal to E, because sometimes we may
Oh, you want to
have
take
to
the
approximate it.
content?
So,
No, but these are all measurable sets, equal to E. I mean,
Oh,
there we defined outer measure because the set we are considering, there is no measurability concept. Here we are taking, we want to talk partition. There already, see, there will exist one partition. E itself is a partition like that. And you just take if you don't have any such, the definition of outer measure, you have to take the union containing.
can you repeat the last point? The net.
No. So the point is, when you define the outer measure,
Your voice is breaking. Can you repeat the
your
last
voice
point?
is very clear to me. I don't know why. I can hear you properly. So what I'm saying is, when you define the outer measure, okay, you have to take the containment. You have to take union containing that, because the measure, the set you are considering, that may not come from the algebra. Okay, you may not have some covering. Okay, here it's not like that. When you have E itself is a cover for this. You take E, union of, I mean, you take the one single set E, that's a disjoint collection whose union is E. Okay, so this collection is non-empty already. So you are taking equal
Yes,
to.
sir.
So you are taking equal
Okay.
to. Okay, so there we define, because there is a problem, because you may not have a collection otherwise. Okay, so the collection
Here
is,
we're considering only measurable sets.
yeah, we are considering only measurable sets. So now we are having
Yes,
sigma
sir.
algebra. We already have only E. So E is a measurable set. Okay, so because of that, it's equal to E. It's not like outer measure.
Yes.
Okay, so this is a new measure. So we want to prove it's a measure. Okay, so this is what is called total variation measure. We'll prove it's a measure. So once we prove, we will call it as total variation measure. Total variation measure of mu. Okay, mu is a complex measure. Then we define a finite measure, which is defined like this. So the proposition is mod mu is a measure, is a positive measure.
Sir.
Yeah.
Also, the disjoint condition is required, or else we can just repeat several EN terms and then
Yeah.
just
So that's why disjoint is there. Yeah.
Yes.
Yeah. Disjoint I have written now. You want to write disjoint like this here?
No, you written it. Yes.
Yeah, disjoint is needed. Yes, that's what I was wondering. But then it's clear disjoint is needed. In outer measure we don't need. There we are taking infimum. Here we are taking supremum. No? So that's why.
Supremum. Yes, sir.
Yeah, correct. So this disjoint is needed. Okay. So mod mu, the total variation is a measure. That's what we want to prove next. So clearly, if you have an empty set, you cannot cover with many things. So clearly, mod mu of empty set is 0. So you have to prove only countably additiveness. Okay. So suppose, so let's take an Fn, because En we want to use for that. So Fn containing in this, Fn's disjoint, okay, disjoint, and union of Fn equal to F. Okay. Suppose we have this, then we want to prove that it's the measure is additive, countably additive, sigma additive. So to prove that, first we want to consider, suppose this is okay. Suppose En, you have an En collection contained in F, En disjoint. I mean, each time I don't want to write. If I say En, maybe I will write the symbol, the disjoint symbol. So such that En equal to F. Okay. I mean, I want to prove we want to prove that summation mod, so summation mu of mod mu of okay, this is what we want to prove. So we want to prove that mod mu satisfies this. So we will prove this side is less than left hand side is less than or equal to right hand side side is less than or equal to left hand side. That's what you want to do. So for that, first we want to consider the left hand side. Okay. So suppose if we have a partition of F which satisfies, which is disjoint, then summation mu of En, mod mu of En. This is what we want to consider. We are taking the supremum over all such partition, and that is what mod mu of F is. Okay. So we take this summation over this. Okay. Now this is equal to summation n equal to 1 to infinity, summation m equal to 1 to infinity, mu of sorry, this is less than or equal to, sorry, less than or equal to mod mu of En intersection Fn. En, so this is n, sorry. So we want to write Fm like this. So this is n equal to 1 to infinity, Fm equal to Fm. Okay. This is F. Okay. Each F we can write it like this. So because of this, we can use the subadditivity and we get that this is less than or equal to this. And this, of course, that sum. So this is equal to summation m equal to 1 to infinity, summation n equal to 1 to infinity. We can interchange the sum because it's all positive. Okay, mod mu of En intersection m. Okay. Mod of that, and that is equal to summation.
You're using sir, you're using n for two different things, or are they supposed to be
No,
the
no,
same
m.
thing?
This is F is indexed with m. This is indexed with n. E is indexed with n. F is indexed with m. Okay, so then I am interchanging m and f. N. Okay.
But you've written that disjoint union of En and Fm is equal to Fn.
Disjoint union of En intersection Fm. This is
Um,
m I have written. If you want, I can change it. This is m.
Yeah, and that is equal to Fn.
Here it's m. Sorry. There I have written m. So here
Okay,
I have
right.
written n.
Yeah.
M. Okay. Yeah.
Okay.
So now m intersection F. Okay. Okay. I have taken any partition of F. Okay. As a disjoint union of En. Okay. Then for any partition, I use this summation and use this property, subadditive property, using the subadditive property of the measure. Not subadditive property. This is just triangle inequality. This is just, I mean, you can, I'm just writing it as this sum. So which is less than or equal to mod mu. This is less than or equal to the supremum, which is less than or equal to mod mu of that. So one way is clear. For the other way, I use the epsilon, whatever. So given epsilon greater than 0, choose. So what do we choose? We want to choose F. F is already there. So EM. Maybe we use some A or something. No, it's okay. EM here, such that mu n of EM. Do we? It's okay. M is m plus epsilon by 2 power n is less than or equal to summation. Oh, I have to choose a partition. Sorry, I have to choose a partition for. I have to choose a partition which depends on n and m. Okay. This pen is not working. choose a partition which is depending on n and n, okay, such that this n and m plus epsilon by 2 power, this is m, okay, so this is summation over m, that is equal to summation, so it should be here n equal to 1 to infinity mod, maybe I'll write it here, summation n equal to 1 to infinity mu of e n comma m mod of this. Okay, is it clear? I mean, whatever I have written, because this mod mu is the supremum over all partition. So here I am fixing m and varying n. I get a partition in for fix m and choose the set fm, and for that fm I get a partition which depends on this n, which varies over n, such that mod mu of this enm plus epsilon by 2 power m is less than this, which we can do. Okay. Now you sum it over all m. Okay, summation mod mu of e nm plus this, when you sum it over, so this will become epsilon. This is less than or equal to summation m equal to 1 to infinity summation n equal to 1 to infinity mu of e nm. But then this is the partition of, I mean, we know that this is a partition of equal to f. So because of that, this is less than or equal to mod mu of f. So the other way is also. I mean, this trick we have done several times, so it's the same thing I'm doing. So first thing we just use the, it's direct. Second thing we use the epsilon. Okay, is this fine?
Sir, in the definition of positive measure, we also include infinity, right?
Yes. So what's the problem here? Here, real measure we don't include infinity because infinity minus.
No, I mean I was just confirming.
Yeah, sure. Positive measure, I mean, Levick measure is infinite, no? So we allow infinity, of course. Here we don't allow because infinity minus infinity can occur. Okay, so it's half an hour. I have another half an hour, 45 minutes. So I will use that 45 minutes to prove. So we want to prove the finiteness of this total variation measure. What we have proved. So if we are given a signed measure, or if we are given, so this is true for a complex measure. Okay, so did I say that? So if you have any, so there is nothing, I mean, we don't need it to be a signed measure or something. This can be proved for complex measure. So if we have a complex measure, then we have a mod mu, which is a total variation measure, and we have proved that it's a measure. Now we want to prove that it's a finite measure, which first we will prove for, the signed measure. Okay, so this proposition is clear, no? So it's a measure is clear. Okay, this is the same idea which we have used several times. Okay, so now we want to prove that mod mu is a finite measure. Okay, so mu is a signed measure, is a real valued measure. Okay, then mod mu is a finite positive measure. So there is no infinity. So this is the proof which requires several steps. Okay. So there is a proof given in Sundar's book. I am just reversing the proof because if you look at the proof directly, then it's not clear how it is proven. Okay. So we want to prove it's a finite measure. Okay. So we assume that it's infinite, then we get into a contradiction. Okay. So assume mod mu of the whole. So what did I use? X is the set we use, no? So there they use omega. I used X. Yeah, I always use X. Okay, suppose it's a real valued measure on X script F. Okay. Suppose mu of X is infinity. Okay, then we want to get into a contradiction. Okay, that's what this is a proof by contradiction. Okay. So first thing is we make several claims. So the first claim is the following. Claim 1. We make this claim. Using this claim, we prove the proposition. Then we prove this claim. But to prove this claim, we make another claim, which is claim 2. And using that claim 2, we prove claim 1. Then we prove claim 2. To prove claim 2, we make another claim, which is claim 3. Okay, like this we go on and finally prove all the last claim also. Okay, that's what we will do. So the claim 1 is for all. So this is the claim for all f in there is a problem in that. So this is my for all f in, this is my script f. This is okay. Script f. Okay, such that mod mu of. So we know that mod mu of x is infinity. There may be other sets containing in that which may be infinity, which may take the value infinity. Okay, mod mu of f equal to infinity. Okay, there exists a partition. There exist sets. There exist C, D, or A, B, doesn't matter. C, D disjoint such that C intersection D equal to T, which is disjoint, and F equal to C union D. Okay, and mu of C is greater than or equal to 1, and mu of D, mod mu of D. Sorry, this is not the measure. This is the mod of mu of C. Okay, this is not the mod mu of C. This is mod of mu of C, and this is mod mu, the measure. Okay? I mean, we should be very careful about all these things. Mod mu of D equal to infinity. So this is the claim I am making. Okay, I have a real valued measure. Then I define the total variation measure. I want to prove that the total variation measure is a finite measure. To prove that, I assume the contrary, that mod mu of x is infinity, okay, infinite. So then assuming that assumption is on the background, assuming that I want to prove, first I prove that for all f in script f, suppose if we have a mu of f is infinity, such that mu of f is infinity, there exists set C and D such that mod mu of C is greater than or equal to 1, mod mu of, I mean, we have set containing in that such that, I mean, one set is infinite, the other set is greater than some number 1. I mean, it's clear what we will do with that. We will iterate it and then finally get a contradiction. Okay. Suppose the claim is true. We will assume the claim and prove the proposition. Then we come to the proof of the claim. Suppose claim 1 is true. Okay. So what shall we do? Then we define. So we take d0 equal to x itself, okay, which is infinite. Okay, we choose d1 union c1 equal to x. Okay, c1 equal to x, such that mu of d1 mod mu of d1 equal to infinity, and mu of c1 is greater than or equal to 1. This is possible by the claim. Okay, iterating, choose d n minus 1 equal to cn union dn with mod mu of cn is greater than or equal to 1, and mod mu of dn equal to infinity. We are just assuming the claim, and using that claim we do this iteration. Okay, so for each dn we have got it. Okay, now we know that, now we can see that now cn's are disjoint. I mean, whereas cn's are contained in dn, cn's are contained in dn minus 1. Okay, and it's clear they are disjoint. Okay, and dn and cn and dn's are disjoint. Cn plus 1 is contained in dn plus 1. dn. Okay. Okay. Now we have got something, and mu of Cn is greater than or equal to 1. So this implies summation n equal to 1 to infinity mod mu of Cn, okay, equal to infinity. Okay, each of them is greater than 1. Okay, this is equal to infinity. Contradicts our first initial lemma, which we may call it as lemma 1. Okay, so the proposition is proved, which is a contradiction. So we cannot have something as, I mean, if that is infinite, then we can iterate to get sets with infinite thing. And because that is infinite, you can find SEN and DN inside, and we can do this. So is this clear? I mean, assuming this claim, you assume this claim, mod mu of f is infinity, then you get a set C and D containing in that such that D has infinite measure and C has mod of mu of D is greater than or equal to 1. That we can do. So once this is done, our proposition is proved. Is this clear? Is this not clear to anybody?
Sir,
Ah.
can you explain once why we have the
Why? Explain what? Say the whole thing again or what?
sir? Like I am asking you to explain why we have a contradiction.
Why we have a contradiction? Our contradiction is
Yeah, what exactly are we
the
contradicting?
lemma 1. Okay, the lemma 1. I will show you the lemma 1. The lemma 1 says that if you have any disjoint collection En, then n equal to 1 to infinity, this is our lemma 1. This is the lemma.
Oh, it's okay. Thank
N
you.
equal to 1 to infinity mu of En. I mean, I'm showing this in window, but you cannot see. I mean, you can see it in the screen. Okay, n equal to 1 to infinity, it's clear. Mu equal to n to infinity, mu of En is less than infinity. For any disjoint collection, we have proved it. We have used this to prove, define the total variation measure. Now we have got a Cn, which are disjoint, and the sum is infinity. Mod mu of Cn is infinity. Okay? So that's what I said. Lemma 1. Lemma 1 is the first lemma. We wish I will number there.
Sir,
Yeah. Ask me.
sir, with lemma 1, you can just take E1 to be X and
Yeah.
I don't. If you take E1 to be X and others to be empty set, then this shows
No. Lemma 1. What does lemma 1 says? It's not mod mu of X is mod mu is a measure. We don't have mod mu of X is infinity. Mod mu of X is a real number. Mod mu of X is real number. It's a positive real number. We are only assuming mod mu of X is infinity. These two are different statements. So you cannot.
yes, sir.
Okay. So these two are different. We always have mod mu of. I mean, lemma says that even if you sum over infinite collection, disjoint collection, then also it's finite. That's what the lemma 1 says. Lemma 1 says something very stronger. So you can't do it like that. So it's good. I mean, we should get confused like that. Okay. Okay. So yeah, so that is why we have to be very careful by using the mod. The mod of the mod of mu of some set, and take the mod that is certainly different from mod mu of that set. Okay, these two are different things. Mod mu is taking the total variation measure, which is taking the supremum over all possible partition of that. These two are disjoint, so we have to be clear. So now the proof is clear, I believe. Let me repeat the proof. We have mod mu, I mean the total variation measure. Let me write it here and erase. Mod mu is a total variation measure. We assume that mu of X equal to infinity. Okay. Then we use a claim which says that if you have any set with infinite measure, that set can be written as C and D, where mod mu of C, this is greater than or equal to 1. And this again, this mu of D, mod mu of D is infinite. Okay. Now we iterate this process and get a sequence with all these things which Cn greater than or equal to 0. They are disjoint set. And that will contradict our first lemma. Okay. So that's what we have to do.
So we still have to prove claim 1.
Exactly. We have to prove claim 1. That is not going to be easy. We are going to prove claim. We are going to use a claim 2. Okay. Now to prove, so the proof is slightly longer. It's not very difficult. It's just as usual in measure theory, it's always messy. So it's also a bit messy. When you want to prove deep theorems in measure theory, it's always messy. So it's just messy, but it's not difficult. To prove claim 1, we make claim 2. So what is this claim 2? So the claim 2 says the following. Suppose we have a f which is in that script f, and mod mu f equal to infinity. Okay, then you define a collection which is called as C corresponding to this f. All those E which is contained in f, okay, and E is something is in this, and mod mu of E, mod mu of f minus E is infinity. Okay, I mean, it's just you have a mu of f. I mean, you have a set with infinite measure for the total variation measure. Then you define a script C corresponding to that f. You can consider all sets containing E such that its complement in f has infinite measure. Okay, that's what we define like this. Okay. So then, I mean, so the underlying assumption is mod mu of f is infinity. Then the claim is you take the supremum over all such set. Okay, supremum of mu of f, mod mu of f, mod mu of E. Okay, E is in the CF equal to infinity. Maybe you call it as equal to infinity. Okay, this is the claim 2. So we will prove claim 2. Before proving claim 2, we will prove that claim 2 implies. First we prove. So this is the claim. Claim 2. We first prove claim 2 implies claim 1. Okay. So then we prove claim 2. Then we are left to prove claim 2. Further, we will assume claim 3 anyway. Before that, let us prove claim 2 implies claim 1. So what does claim 2 says? Claim 2 says that if you have a set of infinite measure, then you can partition it by C and D such that mod mu of C, this mod mu of C as modulus greater than or equal to 1, and the total variation measure of D is infinite. That's why. This is the only claim which has a slightly longer proof. Okay. Now we want to prove that claim 2 implies claim 1. That's what. No, the claim 2 is longer. So this is not longer. This is easy actually. So the claim 2, we have to prove claim 2 implies claim 1. Okay. So the claim 2 says that if you have a set of measure infinite, then you have some collection, and that collection, if you take the supremum of the modulus mu of that, total variation modulus of that is infinite. That's what this says. Okay. So what does it mean? So it's the total modulus of that. Okay. Now see, first of all, that collection has infinite things. So now choose E in CF. Okay. Choose E in CF such that mod mu of E is greater than or equal to 2. Okay. That's possible because the supremum is infinite. So for any given number you can do it, but let us take it for 2, greater than or equal to 2. Okay, and the complement S and F minus E mod mu of this is infinite. Okay, that's what it's implied by claim 2. Okay, we are assuming claim 2 and we want to prove claim 1. Okay, so we are taking mod mu of F minus E is infinite. Okay, now this implies there exists a partition En, okay, disjoint, such that union En equal to E, okay, such that, what does it mean? Such that the we can take that to be strictly greater than that. So we can take that to be strictly greater than that. So such that mu of summation mod mu of En is greater than 2, right? Maybe again here also we can assume strictly greater. Because it's supremum, there has to be one partition which is greater than or equal to 2. Okay. Okay. Now again, let what we did in the first proposition, first lemma, that an equal to en if mu of en is positive and equal to empty if not, okay, and bn equal to en if mu of en is negative and equal to empty set. Okay, then summation, we know that summation n equal to 1 mu of en, which is of course we assume which is greater than 2, okay, equal to summation mod mu of an plus, so there is no mod, I'm sorry. We want to get rid of mod, that's why we define like this. Okay, plus mod of summation mu of p. Okay, so this is greater than or equal to 2. This is greater than 2. Okay, okay. So this implies one of them should be greater than 2. Okay, so take C. Yeah.
Can you just explain why we have that?
One second, let me just write it and I will explain. I will come to that. Okay, union of A and this is mu of C is greater than 1 if summation mu of A is greater than 1, equal to 1. Otherwise, equal to union of B and if summation otherwise, which is the other choice. Let me not write it. Yeah, ask me. Yeah. What is the question?
Sir, like how do we have the existence of that en
That is the
in,
definition of mod mu, no?
script says that?
Yeah, that is the definition of mod mu.
Oh, okay, sorry.
Mod mu is defined like that. Mod mu is a supremum over all such sets. Okay. So when mod mu of E is greater than 2, then there exists En. Okay. So mod mu is defined, that is a total variation measure, which is defined like that. So that is greater than 2 means there exists a partition. That's what it means. Otherwise, we can work with single set or something. We got it. So the point is to get such set like that, we have to go through the partition. That is how it's defined. So then there is a partition which is greater than or equal to 2. Then that partition contains set with positive sign and negative sign. You group the positive sets with positive sign, group the set with negative sign. Okay. And one of them should be greater than or equal to 1 because we have taken that to be greater than 2. Okay. So take D C equal to this and take D equal to F minus C. That's all. Okay. So that's what we have to prove. Mu of C is greater than or equal to 1. Okay. Then mu of C, mod mu of C is greater than or equal to 1. It may be negative, it may be positive, doesn't matter. It's greater than 1. And mu of D, mod mu of D equal to infinity. That's the assumption. Okay. This implication is easy. Let me tell you. I have assumed claim 2. Using claim 2, I have proved claim 1. Claim 1 is this. For all f with mu of f equal to infinity, there exists CD such that C intersection D is in T. That's the disjoint. And f is just the union of C and D. Mu of C is greater than or equal to 1 and mod mu of D equal to infinity. Okay. Anyway, this proof is exactly same as what is given in Sundar's book, but I am going in the reverse thing, which I thought is more comfortable than going through the, because it's very difficult to keep in mind all those. If you go through the claim, I mean the claim in the other way, then it's very difficult to keep track what is happening. So this way, you know that you have this claim, and you want to prove this claim, you make another claim and go on like this. Okay. I don't know how the original proof that came up in mind. I think that's much longer. This is a simplified proof. Anyway, so we have proved claim 1 using claim 2. Now we want to prove claim 2. Now to prove claim 2, we make This is clear. Claim proof of claim 1 using claim 2. Okay. If we assume claim 1, claim 2, then claim 2 is proved. We got the set C and D such that mu of C, mod mu of C is greater than or equal to 1 and mod mu of D is infinity. Okay. Which is just the F minus C.
So here D must be F difference E, right?
Say it again.
D must be F difference E or F difference C.
No. E is gone. You had E. Using that E, you got a partition En. Among that partition, you grouped all the positive valued sets and negative valued sets. So one of them, either positive valued set or negative valued set, that should be one of them should be greater than or equal to 1 because the total variation is greater than 2. Okay. So you have taken one of them, either positive or the negative one, and that is your set C. And then you take F minus C as your D. You want C union D to be F, no? So you are just obviously you have to take F minus C. Okay.
Yes.
Okay. So now to prove claim 2, we make claim 3. Claim 3. Okay. So what is claim 3? So I think that's all. This is the last claim, I believe. Okay. So the claim 3 is the following. If E is whatever, E is in the set, and mu of E, mod mu of E is infinity, equal to infinity. We want to prove that it's not an atom. It freezes. Then there exists set A, B in F, okay, such that this is E. E equal to A disjoint union B, and mu of A, mod mu of A is greater than just mod mu of A is greater than 0, and mod mu of B equal to. This claim 3 says if you have a set of measure infinite measure, mod mu of E is infinity, then you can find a further set containing in E, which again has infinite measure, and it has a complement which has a positive measure. So there is no infinite measure. This is what is called an atom. Atom is something you cannot divide anything. I mean, the atom can be divided, we know. But the original meaning of atom is it cannot be divided. So we use that meaning. So if you have a measure, in a measure space, if you have a set which cannot be divided, means you have a set. I mean, atom in usually atom is something. This is what an atom means. If you have a set, this is something I write, I will erase. E is set in F. Okay, E is said to be an atom if you have any proper subset of E. Okay, F containing E. Then mu of F equal to mu of E, or mu of F is 0. Okay, these are the two possibilities. You cannot divide this set F, further divide this set E. You cannot divide this set E into E1 and E2 with E1 having some positive measure and E2 having positive measure. Okay, either one of them has to be 0. If E equal to, so maybe I will write it like this: E equal to E1 E1 union E2, then either mu of E1. This is for a general measure I'm saying, equal to 0, or mu of E2 has to be 0. That is what an atom is. Okay. So we are saying here that there is no atom for mod mu. Okay. That's what we are saying. I mean, atom is infinite measure. Sorry. We are not saying that if at all there is an infinite atom with infinite, if you have a set with measure infinite, then that's not an atom. That's what we are saying. That's what precisely that statement says. If you have a set with infinite measure, mod mu of E is infinite. Okay. Then we further have set AB such that mod mu of A is greater than 0, and mod mu of B is equal to infinite. Of course, one of them have to be infinite because it's a measure. Okay. So now we prove. First, we prove. How much time we have? Claim 3 implies claim 2. Okay. So how do you prove claim 3 implies claim 2? So claim 3 is following. Claim 3 says, claim 3, we want to prove claim 3. Sorry, we want to prove claim 2. So claim 2 says that you have a set F. Okay. I mean, claim 3 says that there is no atom. Let us remember it like that. Let us remember claim 3 as that. There is no atom for this mod mu. Atom, there can be atom. There is no atom with infinite measure. That's what claim 3 says. Okay, using that we want to prove claim 2. Okay. In claim 2, we want to prove the following. So we have a set F with infinite measure. Okay. Then we define this CF, which is all collection of all subsets of measurable subsets of F, such that it complement as infinite measure. Okay. Then the supremum of some such things is infinite. Okay. So we assume that suppose that supremum is finite, then we want to get a contradiction. Okay. Now we want to prove claim 2. Okay. To prove claim 2, we assume. Suppose claim 2 is not true. Okay. That is supremum of E. It's mod mu of E. What I have written? Yeah, mod mu of E in that CF, whatever I defined as CF, okay, equal to alpha, which is smaller than infinity. Suppose that that is less than infinity. Okay. Then I want to get a contradiction. That's what you want to do. Okay. Notice that if E1 is contained in E2, E2 is in F, E2 is in CF. Okay. E1 is contained in E2, then E1 is also, this is hereditary. This is what is called hereditary property. Okay. E2 is also there. That's because mod mu is a measure and E1 will have a smaller measure, of course. Okay, that we know. If that is a measure, then if you have a smaller measure, that should be smaller than that. This is clear, no? I believe this is clear because mod mu is a measure. Okay, smaller set will have smaller measure. If bigger measure has, I mean, E is defined like this. Let me recall what is CF. CF equal to all those E contained in F such that mod mu of F minus E is infinite. Okay. If some E1 is in CF, then E2 is in CF, then E1 containing in C2 will also E1 containing in E2 will also in CF. Okay. Because smaller set will have smaller measure. So the complement will have obviously infinite measure. Okay. This is clear. Okay. The hereditary property is clear. Now suppose E1, E2 are in CF, then this is a subclaim I'm making, okay? Why it's not writing here? Then E1 union E2 is also in CF. That's because mu of, this is a measure, of course, E1 E2. I mean, we just have to prove it's a finite measure because F has infinite measure. So if we have any set containing in that which has finite measure, then the complement will have infinite measure. Okay, mod mu of E1 union E2 equal to mod mu of E1 plus mod mu of E2 minus E1. Okay, so this is less than alpha. This first one is less than alpha. Second one is less than alpha. This is less than 2 alpha. Okay, which is fine. So this implies mu mod mu of f minus E1 union E2 is infinite. Okay, it's clear. It's closed under finite union. Is that clear? I see a silence. It's not clear whether you are.
Yeah, it's clear.
Yeah, this is fine. So somebody is following. Okay, very good. Okay. So we have defined some CF, which is just all collection of subsets of F whose complement has infinite measure. I have just proved that it is closed under finite union. That's all. Okay, I've just proved that it's closed under finite union. Okay. Now we choose a sequence. Okay. Now choose. We want to prove that the supremum is infinite. That this alpha, whatever we have proved, it's infinite. We are assuming it's finite, and we want to get a contradiction. That's all. Okay. Now this alpha is infinite. Now choose En. En, which is in CF, such that, so because the supremum is alpha, alpha minus 1 by n, that's right, alpha minus 1 by n is less than mu mod mu of E. That's right. And this is less than or equal to alpha. Mod, I mean, by definition, mod mu of En is less than alpha. That is our assumption. Okay. So it's between them. So since we know that, I mean, since this is where the finite union is used. Since the CF is closed under unions, finite unions, here we are only taking two unions. Unions, we assume En is increasing. En increasing. I mean, En is contained in En plus 1. Otherwise, we just take En plus 1 to be, if you have some En plus 1, just attach En to that. That will be a bigger set. So that will be still be greater than alpha minus 1 by n. But if it's closed under finite union, that will be still less than alpha. Right? Is okay? So this, we can assume that it's close, it's increasing. So now mod mu of En increases E, and mu of E equal to alpha, right? Because a 1 by n will go to 0, it's equal to alpha. So we have got a set E such that it's equal to alpha. We still haven't used claim 1. So you can forget all those things. I mean, if we assume that alpha is less than infinity, okay, then we got a set whose mod mu of E equal to alpha. Okay, that's what we have got. And E is, of course, contained in F. Okay. Now that we know that E minus F, mod now F minus E, this has infinite measure. Okay. What does claim 1 says? Claim 1 says there is no atom with infinite measure. Okay. So that's what it says. Okay. Now mod mu of F minus E is infinite. Now, so because of that, choose A, C, A, maybe A, B, whatever you want. A, B, contained in F minus E, such that mod mu of A is greater than 0 and mod mu of B equal to infinity. If you remember, this is what claim 1 says. Claim 1 says there is no atom. So if there is no atom means you can partition the bigger set with the it's a partition. So A disjoint union B equal to F minus E. Okay, you can partition F minus E. F minus E as infinite measure. You can partition F minus E with A and B. such that mu of A is greater than 0 and mu of B is infinite. Obviously, if one of them is positive, I mean, one of them is finite, actually one of them has to be infinite. Let us choose B to be infinite. The other one has some positive measure. Okay, that we can do. Now, we have got a set which has measure precisely equal to alpha. In the complement, we have got a measure set A with positive measure. Okay, now E union A. Okay, E union A is in CF. Since F minus E union A mod of mu equal to infinity. Okay, but mu of E union A mod of this, okay, this is equal to mu of mod mu of E plus mod mu of A. So this is strictly greater than alpha, but by definition this has to be less than alpha, less than or equal to. I mean, that's also right. By definition, that is less than or equal to alpha. This will be, because this is positive. This is greater than 0. Mu of A, mod mu of A is greater than 0. This has to be strictly greater than alpha, which is the contradiction. Okay. Is fine?
Yes.
Okay, we have got a contradiction. So if it is not infinite, there is a contradiction. This is fine.
Yes, sir.
Okay. Okay, fine. Okay, so now we want to get, we want to prove that there is no atom. Now we prove claim 1. So this is, we are left with claim 1. It says that there is no atom with infinite measure. That's what this says. Okay. Now suppose, okay. So suppose this is an atom, then we want to get a contradiction. Suppose, so what is claim 1?
Sir, claim 3.
Sorry, claim 3. Yeah. Good. Because I went it in the reverse way. Suppose there exists an E, an atom E. Okay, I didn't use the atom, so okay. Suppose there exists E with mod mu of E equal to infinite, and for all A, B equal to E, suppose, I mean, this is what we want to contradict. Okay, we want to, again, we are assuming the contrary. Okay, either mod mu of A equals 0 or mod mu of B equals 0. That's what it means. I mean, we are assuming that it's an atom. Okay, atom means that's we want to assume. I mean, we want to prove the contrary. We want to prove that E is not an atom. That B cannot be written as A, disjoint union B, such that mu of A. I mean, one of no, you can no. We want to prove that E can be written as A disjoint union of B with mu of A is positive and mu of B is also positive. Of course, one of them has to be infinite, and we take mu of B has to be infinite. Okay, so that's what we want to prove. Now we have proved that mu of, I mean, now we have assumed we have assumed the contrary, that E cannot be written like that. That means, suppose if E can be written as an A disjoint union B, then either mod mu of A should be 0, mod mu of B should be 0. Okay. Now suppose, so this implies if E equal to disjoint union of n equal to 1 to infinity, okay, then mod mu of En, then there exists a n naught n such that mod mu of En naught, or the other way, Hmm. Right? This should be true, no?
Yes.
Right? Suppose not. Suppose there exists two n1 and n2 such that mu of en is not equal to 0. Then we know that en mod mu of en1 will be greater than 0 because it has positive measure. So the supremum will be positive and mod en2 will also be greater than 0, right? So there cannot exist two set like that. This mod mu, see the point is this. Suppose assume, so let's assume that, if E can be written like that, then there exists exactly one set which has, except one set, everything should have. Okay, let me write this, for example. This is true, right? Okay. Right? Then this implies mod mu of En is also equal to 0. Mod mu of En equal to 0 means for any subset, any supremum, any partition, this is also 0. So mod En, in particular, mod Un is also should be 0. That's clear. So this implies that summation mod mu of En equal to mod mu of. Okay, but we know that this is finite. So this implies mu of is also finite. It's also less than. We know that sum is finite. That's the first proposition we proved, which we used some 2 times already. Okay, because of that, this is true. Fine. This is the contradiction. If claim 1,
Yeah, yes, sir.
claim 1 says there is no atom. If there is an atom, then we know that, this is just I have written it. This is all 0 everywhere else. It's just only one term is there. But then we know that such a partition is smaller than. Sorry, this has to be equal to that. You can even put them out here. Okay. Anyway, that's all the proofs. If you have any doubt, you can look at these notes again or look at the book. The book, the whole thing is reverse. That's all. Okay. Because I thought this is more clear. Okay, so you can look at it whichever the way you want. So this now we have what we have is the following: mod mu is a nice finite positive measure. Yeah, tell me.
In the last before in the equation, summation n equal to 1 to infinity mod of mu of En, right?
Right.
So that is less than or equal to the what is it? This norm.
Correct. This mod mu. Yeah. But then there is only one of them is 0. Everywhere, everything else is 0. So you cannot have any other partition there.
So this is less than or equal to. Oh, okay.
No, this is equal to this. That's what I want to say. Right?
But okay, so
the mod mu
we are taking a general En disjoint En such that is equal to E because
correct.
This is over.
No, you have a E, okay? Then mu of En is equal to that mu of En naught, and everything else is 0. Okay? Then mu of right?
Yes, sir. Yes, sir. Okay. So this is for because
mu of E. See, we find that mod mu of E. This is for E. The supremum will be.
Yes, sir. Yes.
So
This again. Let's see. If you do whatever, you get an En naught. Everything will have mod equal to the En naught. No, there is nothing else which can happen because it's an atom. Okay, you just think about it. You cannot have any other set with positive measure. But it's an atom, whatever we define. I'm getting a lot of disturbance. So, anyway, it's okay. You can ask. Let's finish the discussion. This is clear? You just think about it. Inside E, there is no other set with positive measure except, I mean, you can, there is, it's not that no other set has positive measure. You can have set with positive measure, then the complement will always be 0. Okay. So that implies whatever the sum you have, it is just equal to that. This will imply that mod mu of E is same as mod mu of E. Okay. These two are equal.
Yes.
Okay, that's fine. If you are getting convinced, then that's a finite thing. That's what we have proved in the first proposition. Because of the resistance. Okay. Okay. So now you define a new measure, which is something. Now you got mod mu is a finite measure. Now you define mu plus or minus equal to mod mu plus or minus. Mu is a real measure, and mu of A is less than or equal to mod mu of A. Always, whether it is positive or negative. Sorry, mod of this. Mod of this. So because of this is a positive measure. Now any mu can be written as half of mu plus minus mu minus. No? Yeah. Minus mu minus. So any signed measure, any real valued measure can be written as, so mu and mu plus and mu minus are positive measures. Okay? Finite positive measure. Okay? Any real valued measure can be written as linear combination of positive measure. Finite positive measures. Okay? So this implies any complex measure, which is just real part and imaginary part. Any you know what I have to say, can be written as mu equal to summation mu1 minus mu2 plus I times mu3 minus mu4. Okay, where each mu I is a finite positive measure. Every complex measure can be written like this. So now the time is 21. So I think I will stop here. Okay. So tomorrow Divya will talk about. So is that okay? Is Divya there? Okay. So will you talk tomorrow? Did you? I don't know whether you replied maybe. I didn't check.
Yeah, I will talk tomorrow.
Okay, 6 o'clock. Okay, 6 o'clock. He will talk about dual spaces, LP spaces. Okay. Okay, that's all. Thank you.
6 or
Sir?
5?
Yeah. Say. Ask.
So I was just asking. So unless otherwise mentioned by finite measure, we mean finite positive measure, right?
Finite measure means finite positive measure. When you have real measure, complex measure, we don't have to mention that because that does not take the value infinity. That's the assumption. When that is the case, the total variation measure is also finite, which we have to prove.
Okay. Yeah, thanks.
Bye.
Sir, tomorrow at 5 or 6?
6. No, 5. Sorry. Did I say 6? I'm sorry. 5. 5. I have taken the permission from Krishna to have a longer session. So we can have a longer session, not 45 minutes. Whatever you like. Okay, less than 45 minutes is fine. But if you want to do more, you can take your time. Okay. Okay, bye. And then Friday, the Chaitanya will talk on something. Lusin's theorem. Okay, bye.